Welcome. In this lecture, we'll study a special kind of group, that is a cyclic group. So let us start. Okay. Suppose we have a group, say G is a group and say H is a subgroup of G. If X belongs to H, then this set x to the power n, where n is an integer. Obviously, this is a subset of H, isn't it? Since H is a subgroup of G, H itself is a group. You know that X belongs to H. So X square is X dot X, that is also in H. X cube, X dot X dot X, that is also in H. X inverse is also in H. Inverse square is also in H. So all powers of X will be in H. But if we see carefully, this set itself is a group with respect to multiplication. Why? Because first of all, if you take two elements from this set, say x to the power n and x to the power m, then x to the power n into x to the power m by law of indices, it will be x to the power n plus m. And n plus m is also an integer if n and m are integers. So this is also an element of this set, x to the power n belongs to z. So the multiplication is a binary operation in this set. Similarly, associativity can be easily checked. What is the identity element? The identity element, we know that this is our notation, x to the power 0 is identity. Whatever element x you take from the group, x to the power 0 is identity, and 0 is an integer, so identity is also there in the set. Inverse, of course, there. If x is an element, then x to the power minus 1 is also an element here. So if you take any element from this set, it is of the form x to the power n. So n is an integer, minus n is also an integer. So x to the power minus n is also in the set. And x to the power n dot x to the power minus n is actually x to the power 0. That is nothing but the identity element. So this particular set is also a group. So this is a subgroup of H, in fact, subgroup of G, right? And this set is actually denoted by a set generated by X. This is the symbol. That means this is the set which contains all elements of the form x to the power n belongs to Z. So in particular, if you choose any element X from a group G, then the set generated by X is a subgroup of G and it is called subgroup generated by X. It is subgroup of G generated by X. Okay. Now it may so happen that the subgroup generated by the element X is the whole group G. Then this group is called a cyclic group. Right? So let me define a cyclic group now. Formal definition of a cyclic group. Okay. A group G is said to be cyclic if there exists some element x in G such that the G is the group generated by X. So in other words, we can say, if there exists X belongs to G such that for every Y belongs to G, there exists an integer n such that Y can be expressed as x to the power n. So this is the definition of a cyclic group. Okay, let us see some examples. Examples. Number 1. Say G is a group. Okay, suppose G is a group and E belongs to G is the identity. This is the identity element of G. Then what is this? The group generated by the identity element is actually this, right? So this is a cyclic subgroup of G. In fact, you choose any element for every X belongs to G, subgroup generated by X is a cyclic subgroup of G. Okay. Example 2. Consider this group Z plus the additive group of integers. This is a cyclic group. How to show that? If you can find an element inside the set such that Z itself is the group generated by that element, then I can say this is a cyclic group. Can I have such an element? And that element which actually generates the group is called a generator. Now, does the group Z plus has a generator? Yes, of course. 1 is a generator. See, here the addition is the binary operation. So instead of writing x to the power n, x to the power n means x compose x, x binary operation x, binary operation x, like this. So when that binary operation is addition, it will be x plus x plus x and so on. So instead of x to the power n, we'll be writing nx. So why I am saying 1 is a generator, you give me any integer. Suppose if you give me say 7, you know that 7 belongs to Z. I can write 7 equal to 7 into 1. So any integer, actually there is nothing special about 7. For every n belongs to Z, I can write n equal to n into 1. and therefore your Z plus is a cyclic group which is generated by 1. Not only that, you can argue that it is generated by minus 1 also, because n can be written as minus n into minus 1, right? So this group can be generated by minus 1 also. So this is a cyclic group. What about subgroups of Z? What are the subgroups of Z we know? We have proved in a previous lecture, we have proved that the only possible subgroups of Z are of the form NZ. So multiples of Z. These are only the subgroups of Z. And these subgroups are also cyclic. Here N is the generator. So I can say every subgroup of Z plus is cyclic. Let us check how to check. You choose any subgroup. Let H be a subgroup of Z plus. Already we have proved that if this is the case, there exists an integer n such that your H must be of the form n times Z. And what are the elements in nz? All n multiples of integers. So this is nothing but the subgroup generated by n. So this is a cyclic group. So every subgroup of Z plus is cyclic. Now the question is, Z plus is a particular cyclic group. And we know that every subgroup of this cyclic group is cyclic. So the general question is it true for every cyclic group? If I am given a cyclic group that is not known to me, what are the elements inside it, or whether it is finite or infinite or what, if I don't know, can I say that every subgroup of this cyclic group is cyclic? The answer is yes. Every subgroup of a cyclic group is cyclic. So this is our first result. Every subgroup of a cyclic group is cyclic. Okay, so let us prove this. Okay, so proof. Let G generated by some element X be a cyclic group. Let H be a proper subgroup of G. Why proper? If H is improper, then H will be equal to G. And you know that G is cyclic, so H is automatically cyclic. So there is nothing to prove if H is equal to G. So I have chosen H to be a proper subgroup of G. If H contains only the identity element, that case is also clear to us, because then H will be a cyclic group generated by the identity element. So we are done. Okay. Okay. Now how to do it? If Y belongs to H and if Y belongs to H, then Y belongs to G. But G is generated by an element X. I want to prove that my H is a cyclic group. So what is my goal actually? My goal is to find a generator. As soon as I find a generator, my job is over. So what my argument is, if a Y belongs to H and if L is an integer such that Y equal to x to the power L, then Y inverse is equal to x to the power minus L also belongs to H, right? So what I have achieved? I have achieved that if Y is any element of H, Y inverse is also an element of H. That means H must contain x to the power element of the form x to the power L, where L is a natural number. Because if you say that n is not a natural number, it is a negative integer, then x to the power minus L will also be there. And if L is a negative integer, minus L will be a natural number. Correct? So I can say, therefore, there exists a natural number L such that this is my achievement, such that x to the power that natural number is an element of H. Correct? Okay. Fine. Now what to do? Let us consider this. Let S be the set of all such natural numbers. I know there exists some natural number. Now I am going to choose all such natural numbers. So let S be the set of all such natural numbers L, such that x to the power L belongs to H. Right? This is a subset of set of naturals. So by well ordering principle, this set must have a smallest element. By well ordering principle, the set S has a least element, say M, right? We claim that actually x to the power M is the generator of H. We claim that H is the subgroup generated by x to the power M. This is my claim. If I can prove this claim, I am through. Now, the subgroup generated by x to the power M is definitely a subset of H. That is clear. Clearly, subgroup generated by x to the power M is contained in H. There is no ambiguity, because x to the power m belongs to h, that you know. So any power of x to the power m is again in h, because h is a subgroup. Only thing we have to prove is any element in h is actually some power of x to the power m. That is to be proved. So let y belongs to h, right? This implies y belongs to G, and G is a cyclic group generated by X. So this implies there exists a natural number n or integer n, no problem. We are going to use division algorithm n such that y equal to x to the power n. Correct? Now you have two integers, n and m. What does division algorithm say? By division algorithm, division algorithm, there exist unique integers q and r such that n equal to nq plus r. And what about r? Mq, sorry. Where 0 less than equal to r should be strictly less than m. Because if r is greater than m, then instead of m, we can choose m plus 1. Okay? Well, means mq and r is greater than m, so m can divide that also. So instead of q, it will be q plus 1, the quotient. Okay? Okay, m is the divisor, n is dividend, quotient is q, and remainder is r. Fine. If I can prove that r is equal to 0, then I am through. Because if r is 0, n equal to mq, then y will be equal to x to the power n. X to the power n is nothing but x to the power mq, and that is equal to x to the power m to the power q. Then I am through. So suppose r is non-zero. Suppose r not equal to 0. Then what happened? Then what is x to the power r? X to the power r is equal to x to the power n minus mq equal to x to the power n into x to the power m to the power minus q. Okay. Now, where does x to the power n belong to? See, you have chosen y from h and y equal to x to the power n. So x to the power n, this element is an element of h. Where does x to the power n belong to? X to the power m belongs to h. And any power of an element of h is again in h. So this is an element of h, this is an element of h. So this must belong to h. Now, is it possible? This is not possible because your r is less than m and x to the power r belongs to H. It is not possible because this M is the least element in S. So if x to the power belongs to H, this implies R belongs to S and R is strictly less than M. This is a contradiction because M is the least element in S. Therefore, R equal to 0 and y is equal to x to the power n is equal to x to the power m to the power q. And definitely this belongs to the subgroup generated by x to the power m. Therefore, H is also a subset of the subgroup generated by x to the power m. So, thus H is equal to x to the power, the subgroup generated by x to the power m. Hence proved H is cyclic, hence H is cyclic. This proves the result. So every subgroup of a cyclic group is also a cyclic group. Okay, fine. Now before our intention is to check an infinite cyclic group. If an infinite cyclic group is given to you, what are the possible generators? So before that, we want to prove a lemma. So let us prove a lemma. What is the difference between a result and lemma, or a theorem or lemma? Corollary. I hope you know it. If not, lemma is also a kind of result, but generally we call those results a lemma, which itself is not that important or not that significant, but it is used to prove a more powerful result. So you can say a lemma is a kind of tool to prove a powerful result, an important result. And what is a corollary? Corollary to a result or a theorem or a proposition is something that we can extract from that theorem. That theorem itself has a statement that has some significance. Now, after applying that, you can get something that is called corollary. You can say some kind of extraction from a theorem or some kind of application of a theorem. Not in the broader sense application, but we can get something from that theorem. That is called corollary. So these are the differences between lemma, result, and corollary. Okay, what is the lemma? This lemma says if G, not the identity element, is an element, excuse me, in a group G, then G to the power K equal to G to the power R for KR belong to Z. If and only if, this is the notation for if and only if, G is of finite order, G is of finite order and in this case order of G divides K minus R. Okay, fine. Let us prove. Proof. Remember, this is a both-way traffic. You have to prove that if g to the power k equal to g to the power r for any two integers k and r, then g is of finite order and order of g divides k minus r. Conversely, you have to prove if g is an element in capital G which is of finite order, means g is of finite order, then there must exist integers k and r such that g to the power k equal to g to the power r. What do you mean by a necessary condition and what do you mean by a sufficient condition? This is not a part of the proof, but still I think it is better to mention once. Suppose A implies B. A is a statement and A implies B. That means if A is true, then B is true. In that case, B is called a necessary condition for the happening of A. That means if A implies B, then this B is called a necessary condition. That means when A is true, then B is true. This B is called the necessary condition for A. Now, if this is a both-way traffic, then, or suppose this, if A is true, then B is true. A is called sufficient condition for B. A is sufficient condition for B. Okay. Sometimes sufficient condition is called if condition and necessary condition is called only if condition. Sufficient condition is called if condition. Necessary condition is called only if condition. So we say that A implies and implied by B. So that means A if and only if B. Right? Let me explain it. Suppose you want to purchase a table, right? And I know in the market, the least possible price for a table is rupees 2000. And you have purchased a table. If you have purchased a table, then I know that you should have at least 2000 rupees with you. Otherwise, you could not have purchased. So that having 2000 rupees is a necessary condition for purchasing a table. So you have the table implies you have rupees 2000. Here A is you have the table, you purchase the table, and B is you have rupees 2000. If you have purchased the table, you must have rupees 2000. If you have less than that, you cannot purchase. Other way around, if you have 3000 rupees with you, you can definitely purchase. If I know that the maximum price of a table is say rupees 2500 in the market, and if you have 3000 rupees with you, you can easily purchase a table. So having 3000 rupees with you means you can purchase a table. So here this is a sufficient condition. I have sufficient amount of money to purchase a table. So this is called the sufficient condition. Right? If and only if the government makes a fixed price for some commodity, suppose I know that 2500 is a fixed price, no one can purchase it with less price or more price. So 2500 is the fixed price. So I have the table implies and implied by I have rupees 2500. Okay, fine. So here what is the necessity part? Necessity part means the only if part. First of all, we'll assume that suppose g to the power k is equal to g to the power r for k comma r belong to z. Then we'll show that g is of finite order. So and there is no specific rule that you have to prove the necessity part first and sufficiency part later. You can prove sufficiency first also. There is no hard and fast rule. It is up to you that which condition you are going to prove first. But of course, you have to prove both. So let k comma r belong to z such that g to the power k is equal to g to the power r. Okay. This implies g to the power k minus r is equal to g to the power 0, that means identity. So this readily says that order of g is finite. Okay. And we have proved it in the last lecture that if g to the power k minus r is, if g to the power n is identity, then definitely this n is some multiple of the order. So this is finite. And of course, k minus r is some multiple of order of g. So order of g divides k minus r. So necessity part is proved. Sufficiency. Let order of g is finite. Say order of g is equal to n. Therefore, what about g to the power k plus n? G to the power k plus n is g to the power k into g to the power n. But g to the power n is identity because order of g is n. So this is equal to g to the power k only. So see, we have proved that k plus n and k are two integers such that g to the power k plus n is equal to g to the power n. So we are done, right? So this is true for all k belong to z. So sufficiency part is also over. Okay. Now we are ready to prove the result we desire. What is that result? Our result is let G be an infinite cyclic group. Okay. Then the group G has exactly two generators. Which are inverses of each other. See, for finite groups, this is not possible. If I give you a group, say, this is not a part of the proof. Say, let me give you a finite group, say Z5. So what are the elements? The equivalence classes. Equivalence class of, let me not write equivalence class, simply 0, 1, 2, 3 and 4. These are the elements. And the operation is addition modulo 5. Right? So what are the generators? Can I say that 1 is the generator? Can you express every element in terms of 1? Yes, of course. 2, 1 addition modulo 5, 1 is 2. What about 3? 1 addition modulo 5, 1 addition modulo 5, 1. So 3 times you will get 3. Similarly 4, 4 times. So 1 is a generator. Is 2 a generator? Can you express every element in terms of 2? How 0 can be written? 0 can be written as, you know it, just x to the power 0. That means 0 into 1, you will get it. Okay. Identity element can always be expressed as whatever element you give that to the power 0. So for identity, we have no problem. How can you express 1 in terms of 2? 2 addition modulo 5, 2 addition modulo 5, 2. What is it? 2 plus 2, 4 plus 2, 6. 6 divided by 5. So remainder is 1. So this is actually 1. So 1 can be expressed. 0 is automatically expressed. 1 can be expressed in terms of 2. How 3 can be expressed? 2 can be expressed in terms of 2, 2 itself. How 3 is expressed in terms of 2? 2 plus 2 plus 2 plus 2. So that is 1 plus 2, 3. Right? 4, 2 plus 2, so 4. So 2 is also a generator. Similarly, you verify yourself that 3 and 4 are also generators. So all these 4 elements are generators of Z5. Similarly, if I give you another group, say Z10, what are the generators? Z10 contains 0, 1, 2, 3, dot, dot, up to 9. What are the generators? So you can verify. I'm not verifying. I'm leaving this for you to verify. In this case, how many generators you can expect? You will find that 1 is a generator, 3 is a generator, 1 is a generator, 3 is a generator, 7 is a generator, 9 is a generator. So these 4 are generators here. Why 2 is not a generator? Check. 2, 2 plus 2, addition here, the operation is addition modulo 10. 2 plus 2, 4. 2 plus 2 plus 2, 6. 2 plus 2 plus 2, 4 times, 8. Then 5 times, 0. 6 times, again 2. 7 times, again 4. 8 times, 6. 9 times, 8. So you don't have the chance to get these odd numbers like 1 as 1, 3, 5. These you will never get. 9, you cannot get. So 2 is not a generator. Similarly, you check that 5 is not a generator, 4 is not a generator, 6 is not a generator. So basically, what do I want to say? That suppose Z3, what are the generators? Check, you will find that here your generators are 1 and 2. So you will have 2 generators. So my aim is to say that if you are given a finite group, you don't know how many generators will be. Of course, there is a specific formula, but generators may be more. I can construct a group having 50 generators like this. This is possible. In fact, there is a formula also for getting the generators, etc. We'll discuss on it. So naturally, the question comes that if an infinite group is given to me, what about the number of generators of that group? The basic instinct says that maybe infinitely many generators will be there, but the answer is wrong. Given any infinite cyclic group to you, actually it will have exactly 2 generators and they are inverses of each other. And in fact, you will see after some time, maybe in the next lecture, that there is only one infinite cyclic group of infinite order up to isomorphism. That is Z plus. Okay, fine. So without much ado, let me prove it. So I can delete this portion. Okay, so let me prove it. Proof. So let G generated by some element x be an infinite cyclic group generated by x. Okay. Let y belongs to G be another generator of G. Okay. So you can express any element of G in terms of x and y, both, correct? So I can express y in terms of x and x in terms of y. Therefore, there exist integers L and K such that I can say y equal to x to the power L and x equal to y to the power K. Correct? If this is the case, I can say y equal to x to the power L, but x equal to y to the power K. So ultimately y to the power Lk, right? What have we proved before? We have proved that if there exist two integers in the previous lemma, we have proved if there exist two integers k and r such that g to the power k equal to g to the power r and g is not identity, then g must be a finite order. And order of g divides k minus r. So from here, what can I say? I can say that this implies order of y is finite. Okay, is it possible? If y equal to y to the power Lk, when it will be possible? See, y is a generator of G and G is an infinite cyclic group. So that means if you go on taking y, y square, y cube, y4, it cannot terminate. Otherwise, the group will be finite. So y must be of infinite order. I know that order of y is infinite. Therefore, sorry, I can write since order of y is infinite. Therefore, what can I say? What can I say? I must say that these two powers are same. Because if these two powers are not same, then order of y must be finite by the previous lemma. Therefore, I must say that 1 equal to Lk. Correct? And so this equation, how many solutions are possible for this equation? This solution has exactly two solutions because L and K are integers. This equation has exactly two solutions. What are the solutions? L equal to 1 equal to K and L equal to K equal to -1. These are the solutions. So accordingly, if L equal to K equal to 1, then Y equal to X or Y equal to X inverse. So I'm done. That means if you choose Y is any other generator of G, then either it is X itself or its inverse. So you cannot have more than 2, you have exactly 2. So job is done. Hence, proved. Okay, so this is the proof of the result. So let me stop here. In the next lecture, we'll prove more results on cyclic groups and we'll see more important things. Okay, thank you.